Welcome, everybody. Learning as a hobby here. I wanted to, as promised, supplement my videos on Spivak with the certain sections of Tao's analysis. One, I've already posted chapter 2 for Tao and the solution sets for all of the parts of chapter 2. I've also posted a video on the Patreon page for um, section 1 of appendix A in the book. I still have to continue with that, but I am going to do in this video appendix 7, section 7, and I'll explain why in a second. But just to remind people, if this is the first video that you're seeing, so I'm going through Spivak by calculus by Spivak. Excuse me. Not Spivak by Calculus, but Calculus by Spivak, fourth edition. We just finished up part 2 of the book, which ends with chapter 8. So we finished chapter 8 and its appendix and the solution sets and everything. And before I get to Spivak's construction of the real numbers, I wanted to go through a construction of the natural numbers, some axioms of set theory that we need, and construction of the integers, the rationals, and then Tao also does a construction of the real numbers, but with Cauchy sequences rather than Dedekind cuts. He also has an appendix on the decimal representation of the real numbers, which I want to go through as well. And there's a so as I was going through the book here, there is also a chapter 8, which is on set theory as well. It's on infinite sets. So he talks about like countability, infinite sets, uncountable sets, the axiom of choice, and ordered sets in chapter 8. So I think since I'm going through, like, I'm going to end up, I want to do chapter 8, in other words. So eventually. So I think what I'm going to do is I'm going to do chapter 3 and chapter 4 here. Chapter 3 is on set theory, basic set theory. He constructs it, through an axiomatic system like he did for the natural numbers. Then the next chapter he does the construction of the integers and the rationals. So we'll do that chapter, and then I wanted to do Spivak's construction of the reals with Dedekind cuts, and I'll do also Tao's construction of the reals using Cauchy sequences. I want to do those at around the same time. This way we can compare and contrast the methods. And also, I guess the third method would be, describing real numbers with decimals. So we'll go through appendix B as well in this book. But anyway, since we're going to be going through so much of this book, I might as well finish it. So, but that's my first priority is Spivak. So, I might actually do the sections in Tao once we do all the preliminary stuff, along with the similar sections in Spivak. So this way we'll get, at least like an entry level, not entry level, an introductory level analysis course done along with Spivak, and then I have some other things in mind also for afterward. But yeah, so in this video, this one's going to be kind of short because I just want to do appendix A7, and I'll explain why in a second. But that's what this video is going to be. I'm going to do appendix A, section A7, and then it's exercise set. There's only one exercise in appendix A7, but we'll do that in this video, and then I'm going to post right after that I post this one a video on chapter 3 section 1, the summary of it, which I've done already. I haven't done the exercises for section 3 yet, but the next video will be the summary for section 1 in chapter 3 of Tao. All right, so now that all of that is out of the way, let me bring up the notes for A7, and I'll explain why I felt the need to do this first. All right, so let me see where are my notes. Here we go. Okay, so this is my summary for A7. For A7 stands for Appendix A, Section 7, which is at the end of the book. Now, there's a bunch of things he talks about in the appendix, in Appendix A, but this is like the last section in Appendix A. And this section deals with equality, the notion of, how we define two things being equal to each other. And the reason that that I felt like I needed to do this before I start on chapter 3 is that chapter 3 refers, well, at least 3.1, because that's the only section I've done so far in chapter 3. At least 3.1 refers a lot to one of the axioms that he goes over in A7, the axiom of, what does he call it? The axiom of substitution. So I want to go through this first, and then, like I said, in the next video, which will be longer, we'll go over chapter 3, section 1. Okay, so first things first, here he talks about what we, generally what we mean by equality in mathematics. Equality is a relation that links two objects, x and y, of the same type t. Given two objects, x and y, the statement x equals y may or may not be true. Whether x equals y is true or not depends on the values of x and y and how equality is defined for the class of objects that are under consideration. And he gives some examples. So, for example, in the real numbers, one is equal to 0.99999 forever. Good, that goes on forever. Also in the natural numbers modulo 10, 12 is considered to be what we would say is congruent modulo 10, to 2 modulo 10. Congruent being an example of an equivalence relation, which we'll talk about in the axioms, which we'll talk about in a second. But these are just some examples of some, more, I guess, some less obvious cases of equality of two things. At least for, people that haven't done too much mathematics. So here are the axioms that we want for the notion of equivalence. The first three represent the axioms for something called an equivalence relation. And then we also have an important additional axiom, which he calls the substitution axiom. But let's read through them first. So the first axiom is called the reflexive axiom. And what that says is given any object x, x is equal to itself, so x is equal to x. That's called reflexivity. The next is the symmetry axiom. Given any two objects, x and y, of the same type, if x is equal to y, then y is equal to x. The next one is called the transitivity axiom. Given any three objects, x, y, z, of the same type, if x equals y and y equals z, then x equals z as well. Okay, and then the last one is called the substitution axiom. Given any two objects, x and y, of the same type, if x equals y, then f of x equals f of y for all functions or operations f. Similarly, for any property, p of x, depending on x, if x equals y, then p of x and p of y are equivalent statements. All right, so those are the axioms that we have for equality. And like I said, he refers back to these in chapter 3, section 1 a bunch of times, specifically the substitution axiom, because we need that in order to make the notion of certain set operations to show that they're well defined. But we'll see that, when we get to chapter 3. So just a note here, the first three axioms state that equality is an equivalence relation. I already mentioned this, but if you don't know, that's defines an equivalence relation. The following examples illustrate the axiom of substitution. So there's three examples that he gives just to get make the axiom a little bit more concrete. Let x, y be real numbers. If x equals y, then, for example, 2x equals 2y, and sine of x equals sine of y. Furthermore, x plus z equals y plus z for any z in R. Right, that's just one example where we would use we're using the axiom of substitution. I keep forgetting the word substitution. Okay. Next example, let mn be integers. If n is odd and n equals m, then m must be also odd. That's again by the axiom of substitution, because if n has property p, which is the property of it being an odd natural number, and n is equal to m, then m must also have that property. If we have a third integer k, and we know that n is greater than k, and n equals m, then we also know that m is greater than k. So again, it's just some more examples. Then there's one more example here. This should have been, this is a typo. This should be example. Let me just fix this. This should be 8.7.3. Okay. Let x, y, z be real numbers. If we know that x equals sine of y and y equals z squared, then by the first form of the axiom of substitution, the one that he defines in terms of functions. So we have x equals sine, sorry, where is it? We have x equals sine of z squared. That follows from x equals sine y and y equals z squared. He also says one can also obtain the conclusion x equals sine of z squared more directly by using the second form of the substitution, where you talk about properties that are satisfied. Okay, just a note here. For the purposes of set theory, it is convenient to adopt the convention that the statement x equals y is automatically false if x and y are of different types. We do, however, sometimes override this convention by identifying objects of one type with some object of another type. We will sometimes use the notation x with a triple equal sign to equals y to indicate that a mathematical object x is being identified with a mathematical object y. For example, we've already done this in chapter 2. For example, we identified the natural number 3 with the integer 3, and so on and so on. So we'll be doing things like that. And then, so that's the section A7, and there's only one exercise problem. There's only one problem in the exercise set for A1, which is this question here. Suppose you have 4 real numbers, A, B, C, D, and you know that A equals B and C equals D. Use the above 4 axioms to deduce that A plus D equals B plus C. So here's my proof. Right, so again, just assume the hypotheses. Then A equals B implies A plus D equals B plus D. I should have probably said where that came from. That comes from the axiom of substitution. But I'll just write that up here just so we have it. So this is by axiom of substitution. All right, and C equals D implies that B plus D equals B plus C. Again, by the axiom of substitution. Therefore, by transitivity, we have A plus D equals B plus D, and B plus D equals B plus C. So A plus D equals B plus C. And that's the proof of that proposition. And that's basically the last section in Appendix A. Let me stop the screen share real quick. So like I said, this video was going to be kind of short, but I have coming up I'm going to record right after this video my summary of section 3.1. So keep an eye out for that. But I'll see you guys in the next one.